So yeah, like I said, I'll be doing more like a theory introduction to node embeddings and knowledge graph embeddings. So there won't be any live demos, but there will be some visualizations from encode available that you can use to get more familiar with these concepts. So to jump right into it, so basically what's an embedding like in general, not just in the context of nodes, graphs, or machine learning. And while I was researching this for an article I was writing, a colleague of mine, Ljubica, actually came up with these great suggestions for me to use, which is basically, you can think of as body mass index as an embedding. So basically, a body mass index is used to indicate whether a person is obese or not. So, and you have like various ways to go around detecting obesity, right? So you could measure height, weight, fat percentage, muscle content, waist circumference, and like other things. I was looking at it yesterday, and you can do all sorts of MRI. You can run electricity through your body to get some sort of measures. Or very simply, you could use a body mass index, which is a single feature or like a descriptor that can generally tell you if you're overweight or not. Like, it's not perfect, but it's good enough. And basically the embeddings in general, at least from like my understanding, is that you somehow present some information in a digested way, or that's good enough, right? So for example, in the body mass index, like the typical example is that you have some outliers like American football players, which would all be obese, but they're not actually fat, they have muscle, right? So, but the body mass index would categorize them as obese. So the embedding is like good enough, but not perfect representation of information, basically. And the main thing is that it's dimensionality reduction, right? So in the body mass index, instead of having 5 features to determine whether someone is obese or not, you have only 1. And here in this example, I've found is basically a more simple and like a mathematical approach to show dimensionality reduction. So for example, here you have a cube, right? So you have 3 dimensions, width, height, and basically x, y, z, right? So 3 dimensions. And here it says basically you have 1,000 positions. So basically if every axis only ranges from 0 to 10, then that would mean that each data point can be, basically there are 1,000 combinations, right, or permutations. I never know what's the difference, but 1,000 combinations, different combinations that would be used of the 3 dimensions to describe a data point, right? So and now if you want to do dimensionality reduction, okay, we'll take 1 dimension away, right? And here in this example, we take away the height. So now we have, if you're like a data analyst, you might be familiar with scattered points, which are pretty frequently used to visualize 2D data points. And the idea is here that although you lose some information when you're reducing the dimensions, right, it's here basically what they say, it's without a significant loss of information. So like in layman terms, you could say it's good enough. So here the 2D, removing 1 dimension to represent a data point is still good enough. And the same thing could be done to use only single dimension, right? So you only have the x-axis. And you can see you lose information along the way, but it depends like what is good enough for you and what's not good enough for you, right? So that's very use case to use case specific. And so what does this have to do with graphs, right? Because X, Y, Z axis, that's really cool. But what's the point of using node embedding? So basically what embeddings have to do with nodes and graphs. So first, without going into like technical details, I'll show you, let's talk about a little bit about the motivation. Why do we use node embeddings? And as I said in the beginning, in the two sentences, it's basically you take a network, so basically nodes in a network, right? And you encode nodes in a network such that you preserve a network structure, right? And like I said, basically you take a network, you run it through a node embedding model, and a node embedding model produces a vector that represents each node, right? So here don't make the numbers don't make any sense. I just made them up. But basically these numbers would somehow retain the network structure that's shown on the left. And why do we want to basically have vectors representing nodes or data points? Is because basically vectors are machine readable, like format of data structure, and that means you can use it in machine learning workflows, right? And I'm certain you've seen some examples. Even I've seen, like yesterday I was watching a talk, and basically what they did, there was an HR example, and you have people and their skills, and you embed, basically run a node embedding model on top of it. You get embeddings, and now basically you can cluster your nodes. So in that example, they were using basically you can find nearest neighbor. So they use the KNN. So basically finding nearest neighbors of a certain person for the HR use cases. So that would like fall into the node clustering workflow, right? So I'm definitely sure you've seen some examples of that. But then also probably more cool is like training a machine learning model, right, based on the node vectors, right? Because node vectors, like I said, retain the network information around nodes. And if you've trained any machine learning model in your life, you know that basically you input some numbers into it, and then the machine learning model outputs some number, right? And that could be like 0 or 1, maybe in the case of link prediction, right, where you're trying to predict future links. So that can be thought of as a binary classification. So 1, if a future link is likely to happen between these two nodes, right, and 0 if it's not likely to happen. And there's also the node classification example. So here in this example, we've got a green node and a red node. So this would be like your training data set. And then you're trying to predict which color are the gray nodes. And basically, you can do various things. And one of those things is basically you can train like a machine learning model, a classifier, to predict the colors of those nodes. And when you train a classification model, that's called a node classification workflow. So that's basically why you want to do node embeddings, is basically so that you can support your machine learning workflows with node embeddings which retain some network structure information. So now that we can go back to dimensionality reduction, right? I started with saying that node embedding models are dimensionality reduction techniques. And you're probably used to seeing networks as basically a bunch of bubbles and links between them. But those bubbles and links between them can also be represented with an adjacency matrix. So adjacency matrix is basically a squared matrix where the elements represent the elements of the matrix represent whether the pair of nodes are connected or not. So here in this example, I've got like node D with node C, right 1, that means it's connected. So node D and C has got a link between it. And for example, node A to node C is 0, which means it doesn't have a connection, so there is no connection between them. Right? And obviously you could complicate your adjacency matrix to support weights and stuff like that, but that's basically not the topic of this talk. But the thing is that adjacency matrix can be thought of as a high dimensionality representation of the network. And why it is high dimensionality? Because the adjacency matrix has basically n rows and n columns, where the n is the number of nodes, right? So for example, if you got a graph with 1 million nodes, you've got 1 million rows. Oops, what did I do? Which is not a big deal, right? Because you need a representation for every node or data point in your network. So that's totally fine, right? Having 1 million rows, that's totally fine. But having 1 million columns is basically having 1 million in the like machine learning context. You could say that you have 1 million features that describe your data point, right? And anybody who's ever worked with machine learning models, you know that basically 1 million features would be a bit too much, like to make it workable with most machine learning models, right? So you've got basically the curse of dimensionality, which is too many features, right? And then another problem is, let's say you've got a graph with 1 million nodes, right? So you've got 1 million columns, and now you add a single node to the graph. So now you've got a matrix with 1 million and 1 columns, right? So everything that you did so far, like train the model on 1 million features, that would completely be not relevant anymore as soon as you add one or remove one node, right? Because the number of features is different. And there's also like a possibility of overfitting the model. So here is where the node embedding comes. It's basically node embeddings takes, you could think of it as takes the adjacency matrix, which is a high dimensional representation of a network. You run it to the node embedding model, and you get a lower dimensional representation of the network, right? So here in this example, you can see that n is the number of nodes, right? So the number of rows in your embedding matrix doesn't change. Like I said, because you always need a representation of all the data points or nodes in your network. So the number of rows doesn't change. But what changes is the number of columns, or the number of the features that are used to describe every node in your graph, right? So I've marked it as D. And if you've seen from some examples of talks during these 2 days, is basically the embedding dimension can be arbitrarily defined. So you can take, for example, you've got the adjacency matrix, which has 1 million features to represent every node, and then you have an embedding matrix, which, for example, would use only 64 or like 128 features to represent every node. So basically, there is like a high dimensionality reduction, right? You go from 1 million features to 128, or like 256. Like, I don't know why the power of two numbers are very frequently used, but that's basically just how it is. But you could use other numbers as well if you wanted to do that. And what's the key of the node embeddings? A very important piece of node embeddings is that none of the dimensionality reduction should be manual, right? You never want to have some poor soul trying to come up with manual features that would kind of retain your network information while trying to greatly reduce the number of features, right? And so what you've seen also in literature, it's called a representation learning of nodes. So basically, it's the learning part. So basically, it's interesting from like a machine learning workflow perspective, because like you train one machine learning model to reduce the dimensionality of the adjacency matrix, and then you can use the output of that machine learning model as an input to a classifier, right? So it's basically a workflow or a sequence of one or multiple machine learning models in your workflow. And the interesting thing is that when you say you want to retain the network structure or similarity, right, that's not how you say, that could be ambiguous. So it could have more meanings than just one. But usually what you'll see is that when people say, when non-embedding models say they try to retain network information or network structure, what they are actually saying is that basically nodes that are close in the network should be close in the embedding space, right? So here in this example, I've got two clusters or communities. So I've got the yellow community, A, B, C, D, and then the blue community, E, F, G. And when you've got like a community-based similarity function for your node embedding models, basically you want the communities or basically neighbors in the graph to be also close in the embedding space, right? So if you've used GDS, you might know that fast random projection or node2vec basically can be used as community-based similarity node embeddings. And I also added just one, just so we don't limit ourselves to GDS only. And here I've got, I've seen a lot of people like some notebooks. Let me share basically some experiments I did. I don't know how to share. I'll ask Max to share. But basically, here I did like an example. I used node2vec in this example to generate node embeddings. And then basically I compared the similarity of embeddings for connected nodes, right? So for example, all the pairs of, so what's the similarity of embeddings for nodes that are connected, right? And here, for example, if we use the cosine similarity, you will see that most of the nodes are close to 1, right? So that means that most of the nodes are very similar. So basically, most of the neighbors in the graph are also very similar to in the embedding space. But that's not always the case, right? Because sometimes, like if you take, for example, a social network, maybe you have, like if you have 5 friends, right? Then it's easier to be very similar to all of them, right? But if you have like hundreds or thousands of friends, right? Then there's going to be some friends who you're not that similar to, right? You might have your main group of friends who you are very similar to, but there's always going to be some outliers in your friend, outside your friend group, but who are still your friends, who are not that similar to you. And basically the same thing with Euclidean distance, right? So in the Euclidean distance, it's the opposite, right? So the smaller the number, the smaller the distance between two data points. And you can see also that the peak is around 1. So most of the nodes are very close in the embedding space, and then a bunch of them span out. Oh, okay. And then the other like approach to capturing similarity between nodes, or like retaining the information about network structure, is like retaining not who's close in the network, but what are the structural roles in the network, right? So which nodes in the network have similar structural roles. And the most simple example here I can give you that basically nodes D and F are basically connecting these two clusters, right? So they can be thought of some sort of bridges between various communities, right? So we can say that they have a different role than all the other nodes in the network. So you can see that in the embedding space, actually node D and F are close, and then all the other nodes are close because they have a similar role. So they're like on the periphery of the network. And for example, in this case, they all have two links, right? So, and here are some node embedding models which can be used to capture or encode the structural roles of nodes. And interestingly, if you've been paying attention, I've used Node2Vec in both examples for the community-based detection, community-based similarity, and also for role-based similarity. So basically, by fine-tuning hyperparameters of the Node2Vec algorithm, you can influence which type of similarity should it capture. Yep. Okay. And another very important distinction for node embedding models is basically transductive versus inductive node embedding models. So transductive node embedding models are basically designed for static graphs. So your training and test data set is basically the same graph. So when you're using a transductive node embedding models, it cannot generalize to new unseen nodes, right? So for example, before I said if you've got 1 million nodes and then you add 1, so you got 1,000,001 nodes. So with the transductive embedding models, you would have to rerun the whole machine learning workflow, right? Because the transductive node embedding models cannot generalize to new unseen nodes during training. And for example, both FastRP and Node2Vec are transductive node embedding models. And then on the other hand, you've got basically the opposite, right? Inductive. And inductive models can generalize to make predictions for nodes unseen during training. And basically, I've seen some distinctions when, for example, you've got a growing graph. Some people call that semi-inductive. And then when you have different graphs, so for example, you train your model on one graph and then use it to predict on another graph, then that's like fully inductive, or you can also call that transfer learning, right? Because you take information from one graph and try to apply it on another graph. So that's basically the vocabulary around node embedding models. But what I haven't mentioned is that in all these examples, I've used a homogeneous graph. So basically a homogeneous graph has a single node and a relationship type. So here in this example, we see, for example, we've got only users and friends, right? So it's a friendship network of users. And node embedding models do not differentiate between various relationship types. They just treat them all the same. And they also do not differentiate between different node labels. The only thing that most of them differentiate could be the relationship weight, right? So you could add some weights to relationships to influence the node embedding calculation, but none of them basically differentiate between different relationship types. So for example, if you've got friend and enemy in the same graph, right, the node embedding like FastLP would treat them the same. So what then happens when you've got a heterogeneous graph? When you've got like multiple node types and multiple relationship types. Here I've shown an image of HETIANET. So HETIANET is a quite famous biomedical knowledge graph. As you can see, you've got genes, compounds, diseases, like pathways, symptoms, whatever, and a bunch of different relationship types between them, right? So a gene can upregulate, downregulate, or is associated with a disease, right? And so on. So sometimes you want to capture all the knowledge that you have, right? But still want to differentiate between various relationship types. You don't want to say that upregulate relationship is the same as downregulate, right? The node embedding model should treat them as differently. So what then happens is that you need to use knowledge graph embedding models, which is like a small step up from node embedding models, where you encode both the nodes and also relationship types, right? So as you can see before with the node embedding models, you encoded only nodes, but now you encode both nodes and relationship types. And here I've given like a simple example is, so Tomaz, that's me. I live in Ljubljana, and Ljubljana is part of Slovenia. So you've got 3 different node types, and you've got 2 different relationship types, right? So in the embedding space, you could see that there's a vector representing each node, but there are also vectors representing in each relationship type. And as we said before, basically, if the relationship is present between 2 nodes, then the vector of the start node, so H is defined as head, so the embedding of the start node plus the embedding of the relationship should be somewhat similar to the embedding of the tail node or the end node if the relationship is present. And why do we want to have that? So basically, most or a lot of knowledge graphs these days are you have multiple node types and multiple relationship types, right? And you want to encode all the knowledge that's available in the knowledge graph. And for example, in this case, you want to predict new links, but not only the new links, also their types. So basically, you can think of it as like multi-class link prediction, right? So it's not only a binary if it exists and it doesn't exist, a link between 2 nodes, but also what type of link is between 2 nodes. And similarly, you can also do like node classification by encoding knowledge from heterogeneous graph, right? So here in this example, I've got a citation graph basically of papers, and authors write papers, papers cite other papers, and authors are also affiliated or work with institutions, and you're trying to predict a subject area, right, of a paper. And you can basically encode all this information using knowledge graph embeddings and try to predict or basically improve your machine learning workflows. So that's basically it for my presentation. For the end, I thought I need to, how to say, shamelessly plug in my book. I'm writing a book about graph algorithms for data science. So basically, it's basically a journey how to get from simple cipher all the way to such machine learning workflows as I present. So basically, link prediction or even knowledge graph completion, and I'm almost done with it. So it's 10 out of 12 chapters are done. So that's very exciting. And like I said, I wanted to give you some code so you can play around with node embeddings on your own, right? Because even though this is a purely theoretical talk, I still want to give you some code that you can go through in your own time and play around with it and see what comes out. So that's it for me. And if you've got any questions.
All right, Tomaz, thank you very much for your presentation.
Yeah.
Well, graph embeddings is not really my forte, but I'm telling you, it's so interesting to see you explain all of the theories and how to use it and everything like that. So thank you a lot for your talk. We do have one question here from the audience. So Ahmed asks, besides Node2Vec, are there any other algorithms one should consider?
Yeah, I mean, definitely it's not like one size fits all, right? And it could be that different embeddings work differently for use cases, right? So definitely worth checking out. For example, even the fast random projection that's available in Neo4j is very fast and produces great results. But like I said, but then again, if you want different than community-based or like some mix of community-based and role-based, right, you kind of have to look a bit through. I mean, there's, I would say, like a lot of different node embeddings, and like I'm not an expert.
So they should probably just read your book and get the grasp of it, right?
Like I'm not.
Right. So we have another question here from Tony. So what is the go-to algorithm for heterogeneous graphs?
So basically, there's a library Pykin, which is really awesome. And they provide knowledge graph completion. So basically multi-class link prediction, which is really awesome.
Right.
But also you can look at graph neural networks are also very popular and they're like state-of-the-art node embedding models. So you can have different types of nodes which have different types of features and they pass messages. So basically, I would look at graph neural networks.
All right. So, do you know if there's any like lists that you're where you can find all of these knowledge graph embedding algorithms or anything like that?
Yeah, I mean, for the I'll send you the link for the knowledge graph completion. I can give you the link. I just don't know how to comment, but I'll let you. I'll let you. So there's like a list of, I don't know how many, like 44 different models of knowledge graph embeddings.
All right.
There's a lot.
There's a lot of them. All right. So someone asked about Vivitate. I have no idea what that is.
I think I could, but I have no idea what it means.
Okay.
Let me try to read. No.
So, do you have any suggestions for beginners of data science, graph data science?
Someone asked for a link to the book.
Yeah.
I can give you the link to the book, but if you don't want to pay anything, then I would suggest Neo4j Graph Academy. But also, like, if you want like practical, but there's also cool Stanford has some pretty cool video lessons that are available on YouTube. So if you like, not the most recent one, they deal with more like old school classical graph algorithms like PageRank, and then they also have knowledge graph embeddings, not the back. But the more recent ones are focused like only on graph neural networks, which is basically the thing of the.
I know we have on our YouTube channel, Neo4j's YouTube channel, there's also a series that's called Bite-Sized Data Science.
Yeah, by Claire, right?
Yeah, that goes around everything you can do with graph data science library and things like that, how to use it, import data and stuff like that. So those I can recommend for sure. Thank you very much, Tomaz.
Thank you for having me.